We have this periodic structure, and the structure is a composite structure consisting of two materials, and both materials are described by its Young's modulus and not the shear modulus but the Poisson ratio. And we denote it by Ko, this bulk modulus of the outer material, Go, the shear modulus, and correspondingly Ki and Gi in the inner material. And these bulk modulus and shear modulus are found by the formulas which you know from the compendium. So these are easily calculated since we know the Young's modulus and the Poisson ratio of each of these isotropic materials. For such a structure, we know that we have the following average strain stress relation. Here we have the effective bulk modulus, the effective transversal shear modulus. We'll also T45. This is another shear modulus in another direction. And we have the autoplane shear modulus PL star in these two places in the matrix, stiffness matrix. Here we have the strains given by this expression, and on the right hand side we have the average stresses. Just if you are not used to calculate these strains, just recall that E11, the normal strain in the x direction, is given by this expression, and the normal strain in the y direction, E22, is given by this expression. And gamma 12, which is also an interesting number, is given by this expression. In order to calculate K star, we do as follows. First, we subject this structure to a periodic deformation which is equal in the x direction and the y direction. And what we are doing is the following. We are just considering one unit cell. Since we have a periodic structure, it's just necessary for us to consider one unit cell. And on the left hand side of this unit cell, we choose to let the displacement in the x direction, called u1, be equal to 0. So we fix the displacement in the x direction on this side of the unit cell. On the other side of the unit cell, we choose u1 to be equal to 1. What does this mean? It means that we are stretching the cell such that the displacement is equal to 1. And since we have chosen to let the length of the unit cell be equal to 1 and 1 in the x and y direction respectively, we obtain that the average strain in the x direction is just equal to 1. It's this value minus this value divided by the length 1. Similarly, in the y direction, we let u2, the displacement in the y direction, be equal to 0 on this boundary, this lower boundary, and on the upper boundary we choose u2 to be equal to 1. So the normal strain in the 2 direction is just equal to this value minus this value divided by 1. So this is actually the average normal strain in the y direction. After doing so, we're implementing this into ANSYS. Of course, we have to implement the values of the Young's modulus and the Poisson ratio in this material and this white material, respectively. Then we can perform a calculation and calculate, for example, the energy corresponding to this deformation. So we are stretching this structure in the x direction like this. We are just putting a displacement equal to 1 here, and in the y direction we are putting a displacement equal to 1 here. So we are just stretching it equally in the x and y direction. And we are able to calculate the energy by using this formula. In this formula, C star is just the matrix shown above. So this matrix is just multiplied with the strain vector, and the strain vector is equal to 1, 1, 0, 0, 0, 0. So there is, let me show you. Here you see, due to the deformation in the unit cell, we know that the average strain in the normal direction is equal to 1, in the y direction is equal to 1, and all other average strains are 0. So multiplying this matrix with the average strain vector 1, 1, 0, 0, 0, 0, we obtain just this vector. We know that multiplying a matrix with a vector implies that we take this item multiplied with 1 plus this item multiplied with 1 plus this item multiplied with 0, and so on. So it's only these two multiplications which are interesting. This times this plus this times this is just equal to 2 times k star. In this way we obtain a vector like this, and finally we can, by taking the scalar product of these two vectors, we obtain just 2k star. It's very easy for you to see because we take 1 times this plus 1 times this plus 0 times this is just equal to 4k star, and we are dividing this by 2. So then we obtain that the energy W is equal to 2k star, and therefore k star is just half of the energy computed. So what you are going to do in order to find the effective bulk modulus is just to use this figure, and you are implementing these boundary conditions into the finite element program, for example ANSYS, and calculate the energy. Then you obtain the bulk modulus by dividing the corresponding energy with 2. Let me just make it clear that we have defined that U1, the displacement in the one direction, and displacement in the second direction should have these boundary conditions. What about the displacement in the third direction? It should of course be equal to U3, and U3 is assumed to be 0 for all values of x1 and x2. That means that we should use plane strain in the computation of the two-dimensional problem when we, for example, are using ANSYS. Let me also emphasize that the absolute value of capital Y is equal to 1. This guy is just the area of the cell 1. And as we saw on this figure, we have assumed that the length is 1 in x direction and 1 in y direction. So of course the area here is equal to 1. That's the reason why we don't use the absolute value of y in the calculation of the energy, just because it's 1. So another thing is that we should maybe say some words about how to calculate this average strain E11, also E22, but it's very similar. The average value of a function is just the integral of the function over the cell y and divided with the area of this cell. In this case, the area is just 1, so it's just this integral. And this integral is, in our case, since it's only a square, we have this integral from 0 to 1 in the x direction and 0 to 1 in the x2 direction. And we know from the definition of the strain E11 that it's just the partial derivative of the displacement in the first direction with respect to the variable x1. When we are taking the integral of this partial derivative, it's very simple, because it's in order to calculate this, we just find the antiderivative of this integrand. And the antiderivative of this with respect to the variable x1 is just equal to the displacement u1 itself. So we just insert the values 0 and 1 and subtract these two values like this. We just insert 1 for the x1 variable and 0 for the x1 variable, and take the subtraction of this. And this value is very simple to calculate because it's just equal to 1. Here it's 1 and 0 here. Recall from the figure that we have 1 here and 0 here. So taking the integral of this constant 1 is very simple. It's just equal to 1 when we are integrated from 0 to 1. That's an easy task for you. Similarly, we obtain that the average value of E22 is equal to 1, and the calculation is very simple. Is similar. The average value of the strain gamma 1, 2 is maybe a little bit more tricky. We take the integral from 0 to 1 in both directions as above. Use the definition of gamma 1, 2, which is just these two partial derivatives added together. And we know that the order of integration, we can change the order of integration in any integral. So well, let's do it like this. We first integrate in the x2 variable for the first term and do the opposite for the other term. That's just a little trick which is well, it's not so hard to imagine, but let's just do it. Integrating this guy with respect to x2 is just as above. It's just taking the antiderivative of this, which is equal to u1, and insert these limits 0 and 1 and subtract them as before, and then we obtain this value. And these two values, it's a little bit more tricky to see that they are equal, but they have to be equal because of the symmetry of the problem. We see here that u1 is equal to 0 here and 1 here, and the symmetry in the problem indicates that the solution of this problem should be symmetric. So the value here and the value here should be the same for every value of x1. So that's the reason why we can conclude that this value and this value is the same. So the integrand is equal to 0 there, and similarly we obtain the same for the second term, that these two values are the same value for any value of x2. Therefore this value minus this value is equal to 0 due to symmetry, of course. So then we have this integral equal to 0 and this integral equal to 0, so the sum of these two integrals are equal to 0, and this means that the average value of gamma 1, 2 must be equal to 0. All other averages must also be equal to 0. It's much easier to see this because we don't have any dependence dependence in the x3 direction for any of the other strains. Let us now turn to the calculation of GT star. If I add this average strain vector, 1 minus 1, not 1 as for the calculation of the bulk modulus K star, but minus 1 in this case, and the same values for the rest of these average strains, namely 0, 0, 0, 0. Then multiplying this matrix with this vector would give me, let me just calculate what I get. Then I get this vector, 2 GT star in this position and minus 2 GT star in this position, and multiplying this, taking the scalar product of this vector with this vector 1 minus 1, 0, 0, 0, 0, then I would obtain 1 times this plus minus 1 times minus this, and this will give me 4 GT star, and multiplying this with 1/2 I obtain 2 GT star. So therefore GT star will then be calculated by finding the energy and dividing the energy by 2. So that's what I need to do. How can I obtain this average strain? Let me show you. This is for the calculation of the K star. For the calculation of GT star, let me show you. Here we have it. Then I use the displacement. I put the displacement on the right hand side in the x direction. That means u1. I put it equal to 0. So I fix the values on this boundary in the x direction. On the other boundary, vertical boundary, I put u1 equal to 1. So that means that in the x direction I stretch it. I stretch all the points here out to this boundary. So that's exactly the same as I did for GT star. On the other boundaries I do very similar. I put u2 equal to 0, but on this boundary, but on the upper boundary I put u2 equal to -1. And this will give me the strain vector I'm looking for. So the average strain in the one direction is equal to 1, and the average strain in the normal strain in the x2 direction is just equal to -2. So that was pretty easy. For the calculation of GT45 star, I do the following. Then I need an average strain vector like this. It looks very simple. It's 0, 0, 0, and 1 on the fourth place here, and 0, 0. So taking the product of this matrix with this vector, I obtain a vector, and I'm taking the scalar product as I did before with this vector and multiplying it with 1/2, and then I obtain, you can do it yourself just to check, I obtain 1/2 multiplied with GT45 star, namely this coefficient. So the energy is then equal to 1/2 GT45, and I find of course the value I'm looking for here, and just let me write it down. GT45 star is equal to 2 times the energy. So for this case I have to calculate something. I have to use boundary conditions such that this gamma 1, 2 is equal to 1. And how is this? How can I do this? Well, let me show you. Here, instead of putting some restriction on the displacement in the x1 direction on this boundary, I do the opposite. I put the displacement in the x2 direction equal to 0 now on this boundary, and on the right boundary, vertical boundary, I put u2 equal to 1/2. So the displacement in the x2 direction, that means the y direction, should be equal to 1/2 here. We could have chosen other values, but it makes the calculation a little bit simpler. We do exactly the same, but just changing x2 with x1 here on the horizontal boundaries. We put u1 equal to 0 on this boundary, and u1 equal to 1/2 on this boundary. And calculating the average strain, we obtain that exactly as we did when we were calculating the integrals earlier. We find that this will give us the average strain vector 0, 0, 0, 1, 0, 0. You can do it yourself. Use the method I used above here. Compare with this method, and you will see that this vector is what I get. So when we use these boundary conditions in ANSYS and calculate the energy, we take the energy, multiply it with 2, and then we obtain this effective parameter GT45 star. Let's turn to the computation of this final parameter GL star, which is the longitudinal effective modulus. In order to calculate this value, we should in fact get a situation where the average strain vector takes the form of 0, 0, 0, 0, 0, and 1. Why is that? Well, multiplying the stiffness, effective stiffness matrix by this vector would then give us, well, we will obtain a vector which is 0, 0, 0, 0, 0, and GL star, and multiplying this with the same average strain vector, and with 1/2 we would obtain that the energy, which this is, the energy is equal to 1/2 times GL star. So then we find GL star by taking twice the energy. However, this is a little bit tricky because then we obtain a three-dimensional problem. Why is that? Well, in order to get an average strain gamma 1,3 equal to 1, we have to have a dependence in the third direction. So then we obtain a three-dimensional problem. It's possible to solve this, but it's much easier for us if we can solve a two-dimensional problem. Fortunately, it turns out that the partial differential equations involving this problem will be exactly the same as the partial differential equation that we need in order to solve a thermal problem. Let me show you this thermal problem. Instead of solving the three-dimensional problem, we can solve a thermal problem which turns out to be equivalent by putting the temperature equal to 0 on the vertical boundary here, the left vertical boundary, and putting it equal to the temperature equal to 1 on the right side here. We are not saying anything about the temperature on the horizontal boundaries. And this means that we have a Neumann problem on these boundaries, but it's a little bit tricky to understand this, but don't pay any attention to this. Just do it. Use the thermal problem and solve it by using, instead of the conductivity, which we need for solving a thermal problem, use the shear modulus G0 and the shear modulus in the inner material Gi. It's not 0 actually, it's Go. O is connected to the term outer. And let me just recall what these shear modulus, how to find these shear modulus. I have some expression here for them. The shear modulus is just defined for the isotropic case like this. It's a Young's modulus divided by 2 times 1 plus the Poisson ratio of this material. And you have both these values, the Young's modulus and the Poisson ratio, in both materials, also in the inner material. So what you are going to do is just use thermal problem, and the conductivity you are inserting in the thermal problem is just the shear moduli for these two materials. And when you have found the thermal energy corresponding to this problem. You have solved it in ansatz. The value of GL star is just equal to 2 times the thermal energy. And then you have found also this parameter.